Okay, so this is our chapter 2 where we stop based on the series and parallel of capacitor. Okay. Later on, you can try to do the example based on the series and also parallel, and where I also leave you on one of the calculations part based on the series and parallel, combinations of the series and parallel. So just have a look before we go with the next part of this topic. So on this part where I request you to do on a simplify and find the total capacitance. Okay, you may have a look on this capacitor first. Let's have a look on the series and parallel capacitor. Okay, from this view, you may have a look. You have six capacitance. Okay, you may have a look on this part. You have six capacitance. Okay, 1, 2, 3, 4, 5, 6. So before you simplify your before you find the total capacitance, you need to simplify your diagram. Okay, so since from here you can see we already divided from part one, part A, part B, part C. It means we did some separations based on part A, part B, and part C. So from here you may have a look. You have part A, you have part B, you have the part C. So once you do a calculations of part A, you go on with the next one and the next one. So based on your part A, you may have a look the way they arrange based on the capacitance. So from here, you can identify the way the components they arranged it is based on the series. Okay, and have a look on the B part, this part here. Okay, so when you have a look on the C, is still on the series arrangements of the capacitor. Okay, so you have a look on the C part. In the C also you can see the arrangements of the capacitor in the series form. So once you identify the forms of the capacitance, I mean the flow, how they arranged the capacitor, so you can calculate. So if it's the series means you're going to use these equations. Just have a look. You're going to use this equation to calculate. So for the first part, you can see 1 or 50 microfarad with 130. You just calculate it, then you can find the last answer, what you get. So most of the thing you can find 18.75 microfarad. Okay. Once you're done for the A part, you go on with the B part. It's the same thing because there's the way they arranged it is a series form, right? So you just substitute your value to calculate based on your series equations. Then the last answer you get is 1.875 microfarad. Okay. So this is belongs to the B part. So have a look on the C part. So on the C part, you can see is based on the capacitance 5 and capacitance 6, right? So it's the same flow. You're going to do a series calculations. Once you've done a series calculation, you get the last answer. But in this part, okay, you can convert it to nano, because why I say you can convert it to nano, it still can maintain as a micro, because means always ask you when you calculate, make sure the unit we keep consistent. It's better to keep consistent. Unless the value is too small, then you can be converted. Should be no problem. Okay. So in this part, on the C part, okay, you can see the value is very, very small. Okay, micro means is -6. Okay, nano means is -9. So you can see when you compare the value, the C part, you can get more smallest value compared to the A part, compared to the B part. Okay, so in this part means just put as a nano, unless anyone did in the micro also can be accepted. Okay, once you're done, you have a look. Once you simplify your schematic, okay, your circuit diagram, you have a look on this part. Okay, so in this part, you can see you have a capacitance. It means you already done a simplifications for A, B, and C. So when you have a look on the view, on this view, okay, this one up. Okay, so I just put as a CTC, I just put as a CTB and CT1. It means the total of the part. Okay, so once you have a look on your schematic, or the way, how to say, the way you read your schematic, the way you look your schematic, circuit diagram, the one I said schematic is a circuit diagram. Okay, so the when you have a look on this part, okay, you can see it means the way they arranged it in the parallel form. Take note, sometimes they're using the word parallel, or sometimes they're using the word shunt. Okay, but most of the thing for our EP, we always use the word parallel. Okay, so when parallel, you need to know what the formulas, okay, that you need to substitute to get the answer. So usually when it's come to a parallel, you're going to use the flow, okay, the equations where you're going to add. So this is the one you add from the TA, you add from the TB, you add from the TC, you get the total answer. Okay, based on the total answer, so they have a way I give you in terms of in a micro form. Okay, unless you get in the, maybe some of you can give me the answers in a -5. Okay, take note, some of you could be get this answer directly. Okay, so unless you give this answer, the answer as I inform you, you still can accept. But it's better for you to convert in a scientific, because you learn based on the scientific value. So anytime any calculations based on your electrical or electronic calculator is better for you to keep in unit, scientific unit. Okay. All right. So, and the next part is just a bit of your capacitance. Okay. So a bit of capacitance means is a similar, which is I taught you based on the flux density, which I taught you based on the electrical field strength. It's the same formulas, but this which is related to your capacitance topic. Okay. So have a look on this part. Okay, the electric strength is the same thing in your slide, because Miss just bring up the one based on the theory part. Okay, calculations maybe we can do it later on. You can try. They have examples. Okay, so before that, we just have a look on this part here. Okay, just have a look on your OneNote. Okay, this is where I Miss take it the theory part. Okay, so on this part you may have a look. Okay, this is based on the dielectric strength. Okay, so maybe you heard this term before when I said dielectric strength or even I said flux density. Okay, it's where we go through based on the basic electrical, right? So this is the same thing they try to relate based on your capacitance. Okay, take note, they try to relate based on your capacitance. It's not only is based on your basic electrical field, but it's also related to your capacitance because most of the components, either capacitance, either inductor, either resistor, okay, all the components we have the electrical strength. Okay, so based on this part, they just let you know, okay, the maximum amounts of the field strength that can have a dielectric can be stand with called the dielectric strength. So most of the thing they're just going to say based on the electric strength. Okay, and electric strength is based on the material. Take note, when it's come to your capacitance, is where we always have two parallel. Okay, and these two parallel, they can build up with any type of material. But when I say any type of material means it's based on the semiconductor, it's not based on the insulator or what. They have their, how to say, they have their materials, okay? And the formula they use, you may have a look. Okay, so this is the formula always we can find based on V over D. The way they're using based on the V with the D. This is the one we call as a electric field. And you done these calculations before, some of the example, okay? And the next one is based on the energy stored in the capacitance. Okay, how to calculate? Okay, example, we have based on your electrical field, how we calculate based on your charge. Okay, how we calculate for our work done. Okay, in the previous class. Okay, in the same time, when they ask you to calculate for your capacitance energy stored, it means we say charge, we say discharge. Okay, the term they're using for charge or discharge is related to your stored. This means based on the energy they have in your capacitance. All right. And this part, you just have a look. Okay, those want to write your formulas. Okay, it's better for you to write your formulas. Those have your notes with you, you write your formula. Okay, so example for your energy W, it means for your work part here. Okay, based on energy formula, you use this equation 1 over 2 based on the capacitance times with 2. This is based on the joule. Take note, the unit they measured is joules here. Okay, and how easy it works. At the same time, have a look on the diagram here. Let's have a look on the diagram. Okay, the way they shows you based on the two line here. Okay, example, they just put here as a negative. Okay, ion negative, or we call as an electron. Okay, at the same time, in the opposite direction, and this direction, you may have a look. You have the positive. Okay, it means you have two plates. So it's where we're going to see the electrical, or based on the atom, or based on the charge, is going to move. Okay, the direction they're going to move. Either you're going to move to your how to say, to your plates, okay, or they're going to move forward far from the plates. Okay, example, this one, you have a look on the negative part, the way, the direction they moved the electrons. Okay, you may have a look. At the same time, you have a look on the positive part in the next plate here, based on the positive ion, the way the direction they move on. Okay, so example, this one they call as a force pulling electrons. At the same time, this we call as a pushing electrons. Okay, force pushing electrons. So most of the thing you need to understand. Okay, we can't see with our eyes. Take note now, any currents flow, or we say we have electrons move from one point to one more point, even though it's based on the ion positive, or even we say based on the proton, even we say based on the holes. Okay, so that's the time we need to know. We can't see based on the eyes, but we only can learn based on the theory. Okay, so this one example means ask you to show how is it the flow of your currents flow, or how is it the electrons move. So the only thing that you can do is only sketch. Okay, we can't choose in the physical. Example, I said I have pen, so I can show to you. Okay, I have the pen here. Okay, but in terms of the electron, in terms of the movements of electron, we can't show showed to you based on the physical part here. So most of the thing is based on the theory. Okay. So that's the one I Miss want to finish up based on the electrical strength. Okay. At the same time, I just want to let you know one more thing. Okay. At your team here, just have a look at your team. Oh, okay. Oh, all right. Good morning. So at your team here, just have a look on your team. Okay. Under capacitance, go to your channel capacitance. Have a look on the capacitance. Okay. At the capacitance, you have a look. Okay. Press on the 5 locations here. Press on the 5 locations here. Okay. I just uploaded for you a tutorial chapter 2. Tutorial chapter 2. Okay. I want you to go through the tutorial. Okay. Let's see whether I open the tutorial or not. Okay. This is tutorial chapter 2. Okay. Based on your capacitance. Alright. So this already shows you some example how to calculate based on your capacitance value in case they ask you based on the charge. Okay. Alright. I want you to implement or apply the one you learned for the previous class. Okay. For this tutorial section. Okay. I'm not going to ask you to do all the numbers, but those can do all the numbers is very good. Okay. But I just going to pick up a few numbers from here and make sure you done the tutorial. Okay. So the one I'm going on with the, okay, I'm going to pick up based on the numbers here. Have a look, have a look. This is your chapter 2. Okay, chapter 2. Please do it. And as I inform you, okay, one of your friends asked me whether Miss this is be coming out for the quizzes or not. Yes, it's a one of the quizzes, but Miss can't tell you how many chapters coming out because so far we have 2 quizzes. Okay, some of the chapter will be covered out in the quiz 1, some of the chapter will be covered up in the quiz 2. But this is one of the chapters which will come out for your quizzes. Okay, so I want you to do number 1. Okay, not now. Okay, because today class Miss going to go on with the theory part. Okay, so the first one, do it the first one here. Do it the first one. Okay, do it number 2. Okay, do it number 3. Okay, number 4 is very simple. This is easy for you to do. So I'm going to skip that. Okay, number 5 also easy. Okay, let's go on with this one. Number 6. Okay, number 8. Okay, number 11. Okay, number 12. So I'm not going to give you everything for you to do, but I just pick up a few numbers there, but I want you to do. So those can finish up 1 to number 13 is good, and number 14 is very good. But the one Miss highlighted here is compulsory for you to do. Take note, the one Miss marked here, number 1, number 2, number 3, number 6, number 8, number 11, number 12 is compulsory for you to do. Take note, compulsory for you to do. This is a good practice for you for the tutorial part. Okay, so that's the one Miss want to inform you. All right. Okay, good morning. All right, so let's go with our one more chapter based on the magnetic field. So just have a look on this part here. Okay, so our topic for today chapter, this is we call as a chapter 3. Okay, so chapter 3 is one of the topics also for your quizzes. Okay, will be covered for your quizzes too. Okay, so when we say magnetic field, okay, it's related to magnetic. Okay, so when we say magnetic, it's always stand with the bar, okay, which we have the south, which we have the north. Okay, so besides that, we also can see the directions, how is it works when you have the flux, okay, when they shows you in terms of the flux, the direction of the movements of it, how is it works, okay. At the same time, they also defined a few law, or we say a concept that you need to implement it for your magnetic field. Okay, so let's see, we go one by one here. Let's have a look at the side here. Okay, so just have a look on the side here. Okay, so you can see it shows you based on the magnetic. Okay, so this is one of the diagrams here. Just have a look. Okay, so this is the one we call as a magnetic effects of the currents. Okay, you may have a look the directions, how is it moved. At the same time, just have a look on the next bar here, based on the magnet here, and they shows you in terms of the U. Okay, okay, in terms of the U. So when they shows you in terms of U, you may have a look based on the knot. Okay, so based on the knot, you can see the knot is a what we say as a pole. Okay, the word, okay, have a look on the pole. We say in a pole we have north, we have the south. So when they shows you in terms of electrical field, or they're going to show something happens, okay, between the two magnet bar here. So it's where they shows you based on the pole south, based on the pole north here. So when they have the south with the node, you can see the fields happen. Okay, what we call as a field, magnetic fields happen. So that's the one they shows you in terms of the image here, based on your pictures here. At the same time, they also give you some explanations. How is it works? Okay, why is it we call as a magnetic force? Remember, we also using the word of a magnetic force. At the same time, we also call as a magnetic field. Okay, so the both is this actually one they call as a force because they're going to show you in terms of the line how is it works. At the same time, based on your line, the flux movements also can define it as a magnetic field. Okay, so it's where you have we call as electrical currents, which is we call as a magnetic fields of the current. Take note, the same time at the same thing, based on your magnetic field, or we say as a magnetic field, is where it's based on the properties of the electrical current, which is we call as a magnetic effects of the current. Okay, so because why they say current? Okay, maybe you say, Miss, we only have wow, where we can have the currents here. Yes, you are right. We can't see how to say, okay, Miss have two pen here. Example, I have two pen here. So when I say, okay, example, we just think this is a magnet A, this is a magnet B. So when I say this is a north, this is south. Okay, of course, you can see the field movement when you put the flux around it, right? But how we can say we have the electrical movement? So based on this bar, we can't say we have any electrical movement. But it's only going to work when you have one of the components where we call as an inductor. So where it stand with the coils. So usually they will be circle, or we say based on how many turns we have in a coil. So example, okay, in terms of symbol, this coil we call as an inductor. Okay, so this we will learn in the next topic, but just for your information, why we said related to the current, why we say current is called as a magnetic effect. So when we have this component, okay, based on the inductor, is a coil, how many turns that you have. Usually this coil will be tested based on the magnet. They add a magnet based on the materials. So when you have a current supply into the inductor, okay, you automatically you have the field, electrical fields. Okay, so you will understand this more better when you have the we go on with the inductors topic. Okay, so that's the one Miss want to specific for you. Maybe some ask, why is it we see current, we can't see any supply into the magnetic field, and how we can see current, right? So this is the one Miss want to specific why they say the word current here. Okay, okay, let's go. Okay, this is our learning outcome based on a magnetical field. Okay, and these the terms they always have. Okay, you can have a look later on. Okay, based on the magnetism, based on the magnetic field, magnet, magnetic flux, so on. Okay, flux. Okay, everything. And at the same time, you just have a look on the two part here, based on the law. Okay, this is the one I mentioned to you earlier. Okay, we say as a concept. We say as a concept. Okay, okay, so this the the last two here, Faraday and also Lenz's law. Okay, this is where we call as a equation that we need to understand, or based on the concept how it works. Okay, maybe some of you still remember the end right grip. Okay, so it's based on the law. All right. Okay, so this is a one the outline for the topics. So most of the thing we have four parts here. Okay, based on everything based on a magnetic field. Okay, one is a magnetic force, and one is a magnetic flux density, one is a magnetic force and the field, and the last one is based on the law part. Okay. This is some history of who the founder of the magnetic field. Okay, usually we say as a one of the scientists. Okay, so there's a one the person who found the equation, those found based on the magnetic field. Okay, based on the history. So this is where William Gibble. Okay, so let's see. Okay, so in the magnetics applications, okay, okay, we say component. At the same time, we said devices. At the same time, we say applications. So when we say components, when we say device, when we say applications, they have things that we need to know. So when we say component, is always come into elements. Okay, they only have going to have one components. Okay, or we say one element. But when it's come to device, okay, device means is based on the like a they fully like a package. Is electronics is electronic but it's fully packaging. It's going to work as one of the functions. Example, we say handphone, smartphone. Okay, smartphone is one of the device that we have based on electronics. Okay, but when I say components mean, it's based on a component and element. Okay, what they mean based on the application. So when they highlighted to you applications means you're going to have one more how to say it's not block diagram, but it's more like a sounds like a device. Okay, but we call as an application. So when we say application, it's going to stand a few circuits diagram to bring up as an application. So most of the students try to understand the device and applications like a similar concept. Okay, we can say a similar concept, but they have a difference. Why they say as a device, why they say as an applications. So when they say applications, it sounds look like more bigger compared to your device. Okay, so sometimes you can use the word applications for your device or device to application, but take note, component is smaller compared to your device. Device is more smaller compared to your application because we say applications. All right. So when say application is not a software applications. Okay. Software application, we can say we have many applications we install in your smartphone or we install in your laptop. That is a what to say, that is software application. The one is talking about application is a hardware applications. Okay. So in this part we have okay, we have a generator, we have a motor, we have a telephones. So have a look, telephones also we say as a one of the applications here. We also relay, but take note, relay is actually a component. Is a we have five terminals. Okay, it's a like a look like it's a terminal. It's like a components. Okay, just give me 1 minute. Okay. Hmm. Okay, you may have a look. Okay, this is the one we call as a relay. Maybe later on you can try to Google to find out more details about this part here. But this is how we look. How is it look like? Okay, let me pick up this one. Okay, let's have a look. Okay, they have a slide. They always come in a square shape. Okay, so just based on the terminal, the way they arranged the terminal. So terminal means the one means specific is this link. Okay, so we call as a relay. So they have a many they have a many company based on the manufacturers based on a relay. Okay, so this is how is it look like. Okay, besides that mm, oh, you can find this kind of relay also. Okay, you may find this kind, but this is quite whole one. Okay, but you still can find this kind of the relay too. Okay, other shapes of relay. Okay. Mm, the insider relay I can choose here. Okay. Okay, now you may have a look. Okay, so really they always package or they cover with the black box here. Okay, it is not IC, but we say relay. Okay, at the same time, you may have a look one of the relays where they have like a copper, okay, which is cover up like a coil. This is the one you can see later on like a coil. Okay, is where you have inside the relay. Okay, okay. So that's the one I want to point out. Okay, so after that we have a loudspeaker, we have televisions, we have radio, we have hard disks, we have anti-lock bricks, okay, and so on, okay, until you have the keyboards, okay, even keyboards also we say as applications here, okay. So take note that they have difference between devices and also applications. Okay, so magnetic inductions, they have a two, we say two type. Okay, so when we say two type, one we say as a ferromagnetic, one we say as a paramagnetic. So what the difference between ferromagnetics with a paramagnetics? So once we call as a permanent magnet, one we call as a temporary magnet. Okay, so from here you can identify usually when we say a ferromagnetic is we're going to stand as a permanent magnetic. Okay, in case we sounds we call as a paramagnetic, we're going to say as a short temporary magnet, but you can use the word temporary. At the same time, we will say it's only lasts for a short time. They have a durations. Okay, so that's the time we call as a temporary. So that's the one specific for your paramagnetic. Okay, and the next one, when they say based on a permanent magnetics, based on the ferromagnets, can also attract to the paramagnetic metals by inducting magnetics in the metal. So what they mean, when you have the original, okay, when you sorry not original, when you have the permanent magnetic, okay, at the same time the permanent magnetic can be attract to your temporary magnet. Okay, so it means they can how to say the power, not a power, okay, they can be attracted. Okay, the permanence can be attracted to the temporary, the short time. Okay, so that's the difference between these two. Please take note, in a magnetic we have two types. So unless anyone asks you what's the types of the magnetic that we have, okay, so what is a induction based on a magnetic induction. So these are the two things that you need to know. One is ferromagnetic, one is paramagnetic. Okay, and they have difference. One is permanent, one is temporary. Okay, okay, it's the same thing here based on your explanations. You may have a look on the slides later on. Okay, so let me go with the diagrams here. Okay, just have a look on this diagram. Okay, just have a look on this diagram based on a magnetic field shape. Okay, so this is where we have the magnet bar. Okay, which is stand for the north, which is stand for the south. Okay, at the side of the bar, example this is the one. Okay, so we have the north, we have the south. So beside that, they put as a flux. Okay, they put the magnets flux here. So once they put, they can see how the electrical fields happen. Okay, how the movements of the electric fields happens here. So from here, you may have a look. Okay, just have a look on this image. Okay, this is where they shows you like in terms of your real picture, how does it look like. Okay, so this is where they shows you in terms of the diagram. So this diagram, why they have this one, they going to shows you based on the line. Okay, how is it works. So based on this part, just have a look. This is the north, this is south, and you can see this shows you in terms of the line here. So in terms of the line, just have a look. This line from the north going to your south, same goes to the bottom part here. It means this line going to from the north going to the south. At the same time, they specify the directions of how is it works. So these directions from north, this side, the arrow. Okay, so it means is automatically going to this part. It means they're going to attract. So that's why we have, or this line will be appear. And when this line appear, we call as a line of magnetic flux. So take note, the line, how is it appear. Okay, so this they shows you in terms of a real, this is in terms of the diagram. Okay, let's go for the next part here. Okay, in the next part, it shows you based on the compass. Okay, maybe some using the compass. Okay, those like to travel. Okay, so you may have a look on the compass. So usually based on the compass, you can identify which location, not exactly which location, but they will shows you which direction you want to go. Like example, to the north side, or going to west side, or you're going to go on with the south side. Okay, so this is where you can see is play. Take note based on the magnet bar. Okay, that's why this shows you in terms of the error. All right. Okay, so you may have a look on this part. Okay, actually it's the same thing. Most of the slide they give you the same information, repeated information. So based on this, they shows you based on the pole attract. Okay, based on the direction they attract. Okay, just have a look on this part when you have A diagram, when you have the B diagram. Okay, while you looking the diagram, you can explain it. Okay, you can see when they have a south with the north, it's going to be attract. Okay, what happened when you have the north with the north? You can see the line or the flux going away from the same direction. So it's what happened when you have electrons with the electrons, what happened when you have the protons with the protons. One may say when you have the electron negative. Okay, so it's not going to attract each. Okay, so example, you have the device, not the device, the material A, when you have the material B, which is the same, okay, the same ion, we say the same electron. Okay, so you're not going to attract, but they will move away unless they have this A is the electron and this B based on the positive ion, or we call as a proton, then they have shows you some attractions happen. But in this is based on the ion, but when you explain based on your magnetic field, you take note it means based on the flux line, how the errors coming out, how the errors going out, errors coming in, errors going out. So this is the one you need to explain unless Miss asks you explanations based on your magnetic field. How it works when you have the same knot or you're going to have different south with the knot. Okay, it's based on the flux line. Okay, either it's going to be in a parallel or either it's going to intersections. Okay, so take note about this one. Okay, this is based on the temporary. Why they say as a temporary? I just let you know just now based on the short time. They're going to have a long time, but usually in the short time. All right. Okay, so okay, have a look. Okay, this the one of the part is quite important for you to know. Okay, take note. The one is explained in the earlier is just a theory. Okay, it's based on your line, the flux line, how it works. Okay, some theory, what they mean with the ferromagnetic, what they mean with the paramagnetic. Okay, so this is based on your topics, not the topics, one of the subtopics we call, you need to know based on the equation, how we calculated to get, how to identify the flux density. Okay, maybe you heard this terms before, flux density. Yeah, so based on your magnetic flux, okay, it's the amount of magnetic field based on the numbers of the force, okay, produced by the magnetic source. So what they mean with the magnetic flux, okay, what they mean with the density. Okay, so just have a look on this part here. Okay, when you have a look on these equations, they shows you based on the verb here. The symbols is not a pi theta symbol. Maybe some of you will say that's a theta symbol. Excuse me. Okay. Okay, it's not a theta symbol, but we call as a one of the symbols here when it's come to your flux density calculations. Okay, so have a look on your equations here based on the magnetic flux density. Okay. Excuse me. Okay, magnetic flux density equal to magnetic flux divided by the area. Okay, so they're going to show, let you know the magnetic field. Okay, how much is the magnetic field, and also based on the area they're going to define. From here, you identify the flux density. Okay, and where the symbols of your magnetic field, the magnetic flux, we're using this symbol where we call as a unit verbal. This is the unit. Example, when I say capacitance, we have the unit of farad, right? Same goes to this symbol, okay, for your magnetic flux. Okay, so let's see for the next slide here. Okay, next slide is the same thing. It's not going to repeat back because it just shows you based on the attractions. Okay, the flux density attraction and also repulsions based on the way they moved afar when it have the same knot. Okay, so I'm not going to repeat back based on this slide. You may have a look later on. Okay, this is based on your electromagnetic. Okay, this is based on your right hand rules. So you may have a look on the diagram first. Just have a look on the diagram first. Just have a look on the diagram first. Okay, so you have diagram A, you have diagram B, you have the next diagram. This diagram, figure 4. Just have a look on the diagram. It shows you have like a cooper, okay, where you have something. Okay, at the same time, this shows you a line. flux line. Okay, and the second diagram shows you based on your the way you grip your hand. Okay, based on the pencil or based on the cooper. Okay, or based on the conductor. All right. Okay, and the figure 4 this shows you in terms of a coil. Okay, the coil. Okay, just have a look on the diagram first. Just have a look on the diagram first. Okay, so let's go with the point here. When a conductor is carry a current, so take note. That's why we said when they're using the terms of current is when you have a conductor. Okay, but it should be connected to your supply. Okay, and where they said this conductor going to carry a current. Okay, example you assume this one. Okay, as a one of the conductor that we have right now. Okay, it's where we have a SI is carry current. This means we're going to have a current flow into this material. Okay, as a magnetic field that is a construct about the conductor created. So how is it the line will be created right now? The second one, the second part here, the direction of field is remembered by the grip end. Okay, this is the right and grip rules. All right, so I think everyone know based on the right and grip rules. So this one will come for the next part. Okay. At the third point here, they say figure 4 shows you the field produced by the coil carrying the current. Okay, take note. Figure 3 also you can have the current when it's connected to your supply. Then only we can have the voltage. Then only we can have the current flow. Okay, into your coil. So based on your first diagram here, just have a look on your first diagram here. This first diagram here. Okay, so based on that, okay, just assume you just assume this one as a conductor that we have. Okay, and where this shows you a magnetic field produced by the currents. Okay, and the field proportional to the current. So in this direction, based on your directions, okay, this just means assume. Okay, so I'm going to have the currents flow. Okay, I have the currents flow from this direction. Okay, and at the same time, you're going to have a line. Okay, it means we call as a magnetic line. Okay, in terms of the circle. Okay, in terms of the circle. Why we have in terms of the circle? Why means we cannot have square shape, is it? Or we cannot have a sawtooth, we cannot have the triangle shape, is it? So take note. So when is actually based on the design, based on the shapes of your conductor. Okay, example, your conductor built out based on the square. Means you don't have a square. Okay, we have a square. Then your magnetic field, the way you're going to sketch your material should be square shape. Okay, so the one they're giving you to as an example is based on the pencil, the circle one. Okay, it means this one, the circle one, the round one. Okay, so it's where they also let you know we have a current flow. It means from this point to this point we have a current flow. So example, we can think note this is like our wire. Okay, like example how we connected the components with the other component. We use a jumper, we use a wire. So we just assume this is a wire. So when you have a current flow from this part going to this part, automatically you have the magnetic fields. Okay, you're going to have the magnetic field based on the direction. So in this direction, you need to know, okay, either how to know whether this going to come out going on with these directions or is going to the next direction. I mean, based on the right hand side or left hand side. Okay, so that's why we're using the rules of the and grip. So right and grip. That's the reason we're using this rule. Okay, so when you the way you grab, so those you using those have a pencil with you, you can try. Okay, so you have the pencil with you, you just grip your hand. So the way you grip, either you can grip in this part, okay, in this side, or you can grip on this side. It depends how you grip your cooper. So example, based on your diagram, I shows based on your diagram. Example, the grip on this side. So I can know the current flow will be from here to here. Unless I grip my hand, I say the current flow from this part, I will know the magnetic field, how is it move. Okay, so it means when the current flow from this direction, so the magnetic field will be in this side. Unless the directions from this side going to this side, so the magnetic field going to move in this side. Okay, so it means this is the one you can see right now. Okay, so it's where how you have the hand grip rule. I think most of you, I think not most, I think everyone know based on your hand grip. So later you can try, unless I say the current flow from this side or current flow from this side. So the way you take note. So it means your thumb, this thumb is the directions of your current. Okay. At the same time, you just have a look on the coil here. The figure 4 here. Just have a look on the figure 4. So in terms of your figure 4, they not shows you in terms of conductor, but they shows you in terms of a in terms of a coil. Okay, example. Okay, you just have a look. This is my microphone. Okay, so you have a look. So we just think this is a coil. Okay, we just think this is a coil. So when I say coil, of course, we need to know it's belong from what type of materials. Of course, it always stand for copper or different type of material, which we can have a current flow. So in terms of this, okay, I just put here. Okay, so example, this is our coil. So make a circle here. I make a many turns here. So when I make many turns, okay, when we take out, okay, it looks like this. Okay, will look like this. It same goes to your picture number 4. Just have a look like this. Okay, so this one, the white one, you just think that is a copper. Okay, so from here, example, I say a current flow. So my current flow, example, I say going to have from here. Okay, current flow from here. So when I say current flow from here, so you need to know the directions, how is it works based on your magnetic field. The movements of your magnetic field inside, I mean, not inside, the way they're going to describe based on the coil, this part of the coil. Okay, so that's the one. Okay, that's the one that shows to you based on this part here. Currents flow from this part. Okay, they have one more part, but they just focus on this one. Okay, the way they have two coil. Of course, when you round it, you will have two sides. One from this one the next one. Okay, so they come out in terms of the circle. You have the current flow from here. So current flow from here, example from here, you need to know the way you grip it, the electrical field movements, how is it works. So it means you're going to move onwards this direction. So onwards this direction, you can see. Okay, same goes to this part. Okay, so that's the reason we're using the terms of the current. Okay, so when I said magnetic field, why, how we related to the current. So you need to know why they are related to the current. Okay, when we have supply, then only we can have the current. So based on the magnetic field, how it works. Okay. Okay, have a look on this one. Okay, you may have a good idea. Okay, this is only they shows you based on the coil. Okay, this one they shows you based on your where you have the magnetic. Okay, based on the core. What they call the materials. What kind of the materials they're using it. Okay, just have a look on the image first. Just have a look on the image first. Okay, just have a look on the image first. This one. Okay, at the same time, just look. Okay, at the same time, you just have, we have 2 points on this slide. Okay, one point, the first point they say based on your coil. It means this one. Now, this is your coil. Okay, and where they say as a ferromagnetic material. So when it's ferromagnetic material, you need to know, is it it's permanent or is it temporary? It means it's a short-term material. Okay, and most all the flux is configured by the core. So what they mean with the core? This is the one they mean with the core. So the core can be not necessarily will be stand with the iron core. They can be a different material. Okay, but the one they give in your slide example, they just specific for you. You have a core. Okay, and this core is stand or built out from the iron. Okay, at the same time, they shows you based on the directions of the flux. Okay, how is it works? Okay, so based on the second point, they say a small amount. So it's where they call as a leakage flux. Okay, pass through the surrounding area. Sorry, the surrounding hair. So hair means free space, right? Free space. So in terms of that, they shows you. Just have a look on the pictures here. Just have a look on the pictures here. So the first one, you have the coil. This is the coil, okay, and you have the current directions, okay. At the same time, you have the core, the iron core, and the iron core here is surrounded by the coils. Okay, they round up, they circle it by the coils. At the same time, they shows you based on the core flux, which is represent this error. Okay, the line here, and this line where we call as the length of the magnetic part. Take note, this is the length of the magnetic part, and so sometimes we need to calculate how much the length of the magnetic part, because it will be affect your current too. Okay, so based on this part, they say, okay, leakage of flux means is based on the current flow here. Of course, you will have a something will be leakage out. Okay, no matter what. Example, what to say, sometimes we can't see with our eyes, okay, but we can see something happens like a radiations form. Okay, in terms of radiations form, we can't see, but we can see something like a, in terms of like not a wave, but you can feel it. Okay, you can't see, but you can feel it when you based on the radiation. The same goes to your coil. Okay, we can't see exactly everything. We have the magnetic field inside the coils here, but we can say they also have some leakage based on the flux leakage. So when I say flux leakage means it's going to affect based on your iron, based on your copper. So that's the time you have the core flux part length here need to be calculated to define the value of your uh, magnetic field part here. Okay, your magnetic flux here, how much. So that's the thing we need to take note based on the length, magnetic length. All right, so maybe we go with the next slide here. Okay, have a look on the next slide. Okay, just think this is where we have the length, we have the coils. Okay, the movements of your magnetic field. Okay, so have a look on this one. In this part, they let you know the flux density. Okay, the equation, the same equations what you saw in a previous slides. Okay, the same equation actually. Okay, so in terms of here, you just have a look on the image here. Just have a look on the image here. Just have a look on the image here. Okay, in this part, okay, one more things I just want to specify for you. Okay, is where the unit of this one. Okay, the flux density unit. Flux density unit, the unit they're going to measure for your magnetic field. Okay, for the magnetic field is a T Tesla. Okay, the unit is a T. Okay, and where the T you need to know and for how much equal to how much. So it's going to equal to 1 Weber slash meter power of 2. This is the unit. Okay, why we have this unit, why we need to know 1 T equals to 1 WB per meter power 2, because you need to convert. Sometimes they request you to convert the flux density to the value of Weber per meter. Okay, so that's the reason you need to take note based on the way they converted this unit. Okay, and have a look on the image here. So when you have a look on the image, okay, this is where we have the part of the, in terms of the coil. Just now, this one, the coil, this iron coil, this one, okay. So this is the one we have measured based on density of the flux, how they calculated. So this the dimensions of the coil, how much is it the coil? It means based on the coil, based on the coil, iron here. So this one with the directions. So based on these directions, we need to take note based on the wider, we need to take note based on the length. At the same time, okay, once we get the area, we need to define the magnetic flux, or how much is it the magnetic flux. So once we defined the magnetic flux, easy for you to us, pretty easy for us to calculate the flux density. Take note to calculate the flux density. Okay, so that's the one. Okay, they're using this term to calculate. This shows you in terms of the core, square shape core. Okay. Okay, just have a look this one. Okay, I think we take a 10 minutes break, but before we take 10 minutes break, we go on with this example. First one of the examples here. Okay, have a look on this part here. Okay, just have a look on this part here. Okay, so on this diagram, okay, let me read for this one first. For the magnetic core of a figure, this figure, okay, the flux density at the cross section is 1. Okay, the cross section 1 is B1 equals to 0.4. Determine the B2. So it means from here you can identify, it means you have two flux density. One they are referring to the B1, one they referring to the B2. Okay, at the same time, remember all the short term for the formula. Okay, means okay, any short term, what the mean short term means, okay, A stand for what, okay, this shape like this one is stand for what, is a magnet related to your flux, and the B stand for what. So when they say B means is you need to know it stand for flux density, because in this question they ask you based they just ask you determine B2. So when they say B2, you need to know the B stand for what. So that's the reason it asks you, you remember what B is stand for what. So B stand for your flux density. On this one, this shows you you have a core here. Okay, this core, they now highlighted to you what type of the core, what materials of the core. Okay, but they specific for you area. Okay, and where from these questions you can know you need to have two area at the same time. They defined it. You have a two flux density. Okay, so just have a look on this part. Okay, why we should find a two flux density? Okay, the reasons why the core they build up is not the same shape. Okay, sometimes they build up the core with the same shape. Example, what I mean same shape means okay, example, just assume this is the core. So it means the flux, the line, the currents flow, okay, the leakage currents, okay, into this core, okay, will have the same dimensions, okay, they have the same wider, they have the same length, okay, so that's the one we can only maintain with the one flux unless they say the dimensions is not the same, then you be careful. It means this one, this size, these dimensions is not same with these dimensions. Example. So in the question they given to you right now, in the example, you can specify they have two. I mean, you will have two dimensions, different dimensions. One for this one, and one more for this one. Okay. And at the same time, they already let us know that we have B1 equal to 0.40. They already highlighted for us B1 equal to 4.4, 0.40. All right. So the thing they ask is B2 how much. So at the same time, they already specific for us the area A1 area is how much. Okay. Take note, any question, no matter for what chapter, either for the chapter capacitance or the chapter magnetic field, take note the formula. Once you get, okay, you try to relate which equations, the suitable equations that you need to use for the questions. Okay, so for this one, we need to know which equation that we need to substitute. So from here, we need to know flux density over the flux divided by the area. So this is the one formula that you need to apply it. Okay, so I already know the A1 is 2 times 10 power or minus 2. Okay, I already know the answers for B1 is how much. So from here, I can find the flux. How much is the flux? Okay, so once I can define the flux, I can define the B2 value. Okay, so how is it? Because the flux will be the same. Okay, so example, you have a look on this one, the solution. Even you already have the solutions here. So B1, this equation from here, mm, this is the basic equation. Okay, so when you do your maths, of course, you know how to convert your equation to define the value of flux, right? So you have these equations. So these equations equal to your B1 plus A1. So you already have the B1 answers, sorry, you already have the B1 parameters value. Same goes to your A1 parameters value. Then you just times. So 0.7 is 0.4 is the flux. This one. Okay, and the area where they already specific for you, this is the value, the parameters value, okay, which is 2 times with 10 power minus 2, okay, meter. Once you times, you get this answer. You will get the right answer. Okay, so 0.8 times 10 power of 2, but the unit you're going to measure based on the verb WEBR, okay, or we just put in the short form WB, okay. And since all the confines to the core, okay, the flux at the cross section 2 is the same as the cross sections 1, okay, take note, they already specific for you the cross section 1 and cross section 2 based on the flux. It's the same flux. So when they say the same flux, you're going to use the same unit. Even though this is they highlighted to you the same because in the solution. Without the solutions, you also can define that the flux will be the same. Okay, so you just substitute your equation in this formula, you can get the last answer. Okay, so B2, you need to find your B2. Okay, you already know your flux is how much your flux is from here. Okay, it means 0.8 times power minus 2 divided by the area. So in terms of this diagram, they already specific for you the value. It means the parameters value for the area. You just substitute, you just divide. So 1 times power 10 power minus 2, you get the last answer stand for how much. At this time, they shows you the B in a 0.8T. Okay, is where you defined it. The flux density value 0.8T. And the same time, you can convert this one in the WB per meter power 2. Take note, the value 1T equals to 1 WB per meter power of 2. Okay, so this is a simple equation, okay, a simple calculations, all right, based on the flux and also flux density. Okay, the next one is based on the magnetic circuit. So before we go on with this one, we just take a break for 10 minutes. Okay, we take a break for 10 minutes. Okay, quiz one, once Miss teach you the chapter. So once Miss Kawa based on the inductor, once Miss Kawa based on the magnetic, once Miss Kawa based on the DC circuit, then we will have the quiz. Okay, usually if Miss can teach you very speed, then we can have before your midterm semester. Unless Miss go on how to say slowly and steady, then we will have after the midterm. So after the midterm means it could be in a week 8 or can be in a week 10. All right. So just take a break here. Let me stop record first.